On Thursday, we learned about another type of simple harmonic motion, specifically the pendulum. We learned that the period of a pendulum, the time that it takes for one complete back and forth motion of the pendulum, is equal to 2 pi square root L over G. Lots of people thought that the initial angle would matter for the period of a pendulum. Lots of people thought that the mass of the bob on the end of the pendulum would matter. It does not, at least at relatively small angles that we'll be dealing with. The only thing that affects the period of the pendulum is the length of the pendulum, the string, and gravity, 9.81 versus whatever it is anywhere else that you're trying to find the period of the pendulum. If you go to a swing set, and you've all done this, maybe not noticed this, but you go to a swing set and you start pushing somebody on the swing set, maybe your little brother or sister, or maybe it's just a friend or whatever, so pushing somebody on the swing set, you know that intuitively you push it at a constant rate, right? But what happens to the amplitude of that vibration the more you push it? Well, it keeps going higher and higher and higher, right? So you might start off like this, but then you keep going higher and higher and higher, right? But you know that you still, in your mind, have this pace set at which you push it. So the period, the time that it takes to come back to you, isn't changing, even though the displacement or even though the angle is changing. Those things don't matter. The only thing that matters at relatively small angles is the length of the pendulum and gravity. Now, we also learned how to rearrange this, and it's a little bit tricky. Solving for L is the easiest one. To get G, we need to solve for L first and then get G. Let's go through that process, and then we'll go over the questions that we were working on Thursday. We want to find L. So how do we do that? What are we going to get rid of first? 2 pi, right? And it's multiplied by the square root L over G, so how do we get rid of it? If it's multiplied, we divide, right? So we're going to say T over 2 pi equals the square root L over G. Now what do we get rid of? The square root. And how do we get rid of that? Square it. So it becomes T over 2 pi squared equals L over G. And finally, if we want to solve for L, now we're going to get rid of G. It's on the bottom. We divide it by that, so we're going to get rid of it by multiplying. So it becomes L is equal to G times T over 2 pi squared. That's the equation for L. Now, if we want to solve for G, we go from this step and then do what? Not swap G and L, no. G has T over 2 pi squared multiplied by it. So how do we get rid of that T over 2 pi squared? Divide. And it looks a little bit ugly when we do that, but it becomes L over T over 2 pi squared. So look, if we look at this as one term, this entire thing as one term, then we divide by that entire term, and we end up with this equation. Looks ugly, doesn't really matter. Sub in your numbers and solve for it. My suggestion, as I told you on Thursday, was multiply these two numbers first, then divide, then square, and then say L over whatever we get when we do all that math. All right? Good. That's it, basically. I want to take a look at the 3 questions we're working on Thursday, page 379, 1 to 3. Let's do 1 or 2 of these questions. Preference? No preference? The answer 3 was 1.79 seconds. Somebody said number 3? Okay, you want to do number 3? Okay. Let's do number 2 as well, actually. Let's do 2 and 3 here. So 2 says a pendulum, swings at a period of 5 seconds on the moon where the gravitational field strength is 1.62. We want to know the pendulum's length. So what do we got here? The period is 5.00 seconds. The field strength, little g, is 1.62 newtons per kilogram. What are the other units that we can use for field strength? Meters per second squared, because it's the same as the acceleration due to gravity. We want to find L. So we say T is equal to 2 pi square root L over G. Take the 2 pi over by dividing. I'm going to go through this process even though I just did it, just to refresh your memory on it. Take the square root over by squaring. And then we take the G over by divide by L divided by G, take it over by multiplying. So L is equal to G times T over 2 pi squared. So what do we got here? Be careful you don't make G 9.81. It's 1.62 times T, which is 5.00 seconds, divided by 2 pi n squared. So let's figure that out now. Let's do what's inside the brackets first. 5, actually, let's do the 2 pi first. 2 times pi equals 6.28. Let's say 5 divided by that number. Inside the brackets, we get that. Square it. And then multiply it by 1.62. And we get 1.03. So on the moon, in order to have a period of 5 seconds, this pendulum would need to be 1.03 meters long. Right? Now, question 3 says, what period would a 30 centimeter long pendulum have on Mars where the field strength is 3.71? This one's easier, actually. Usually they get harder. For number 3, we're going to say t is equal to 2 pi square root L over g. What do you got to be careful of here? It's not a hard question, but you do have to watch out for something. Centimeters to meters. So we're going to make L 0.30 meters divided by 3.71. And when we do that, here, let's get the number. Let's do this here. 0.3 divided by 3.71. Get the number inside the square root sign first. Then let's square root it. And then let's multiply it by 2 times pi. We're going to get a value of 1.79. Good? I would suggest the hardest part of a question like this is rearranging. Otherwise, it's pretty straightforward. There's really only 2 variables that you can sub in, right? So it's just a matter of rearranging for the most part. Now, how could we throw a little twist in this to make it just a little bit harder? What if question 3 didn't say what period would this pendulum have? What if question 3 said what frequency would the 30 centimeter pendulum have? What would you do? We haven't learned an equation for the frequency of a pendulum, have we, or have we? Sorry? Yeah, and how do you convert it to frequency, Ben? Right. So do what we just did. Do exactly what we just did, even if you're looking for frequency. And then once you find the period, you're just simply going to take the inverse of that. 1 over the frequency gives me the period. Good? Okay, we're going to have a quiz on this tomorrow. It'll be 1 question. Be prepared for units, right? 30 centimeters, 0.3 meters. Be prepared for rearranging to solve for L or G. Be prepared for frequency as well, like I just mentioned to you. Otherwise, basically everything. This is your practice quiz, right? There's not going to be any trick to it other than what you see up here, other than perhaps a frequency in there, possibly. All right. I'm going to spend just a few minutes right now talking about a phenomenon called the resonance. First, before we do that, we have to define another term that's related to resonance called resonant frequency. The resonant frequency of something is the natural frequency at which something wants to vibrate. I put wants in quotation marks because, of course, an inanimate object doesn't want anything, but it naturally will vibrate at a particular frequency. If I knock on your desk, you hear a sound. That's because the desk vibrates at a natural frequency. It has a natural frequency at which it will want to vibrate, and that's the sound that you hear. If I knock on the board, it's a different sound. It's because the board has a different natural frequency at which it wants to vibrate. If I put the meter stick over the edge of the desk and do this, it vibrates back and forth at a particular frequency. If I change the length of this meter stick by bringing it in, then the natural frequency of the meter stick changes, hence the frequency at which it vibrates is different, hence the sound that you hear is different. Natural frequency at which it wants to vibrate. You guys, those of you who went to West Edmonton Mall, were all in my bus, the bus that I was driving. And then for some of you would have heard, if you were closer to the front of the bus, there was this wicked sound, this humming sound that was coming from left side of the dash at highway speeds, like 105, 110 kilometers per hour. How many people heard that? It drove me nuts. Something inside the dash had a resonant frequency that corresponded to the engine frequency at highway speeds. That's why we heard it at roughly that speed of 105 to 110 kilometers per hour. Everything has a frequency at which it wants to vibrate. Everything does, including pieces within the dash. Now, if those pieces within the dash are attached properly, then everything's good, and you're probably not going to hear the vibration. But if they're free to move like the end of that meter stick was, then you're going to hear that vibration. That's why we didn't hear it when we were in the city traveling at 50 kilometers per hour, but we did hear it when we were on the highway traveling at 110 kilometers per hour. Everything has a natural frequency at which it wants to vibrate. Everything does. Now, resonance is a phenomenon whereby there is a force applied at a particular rate, at a particular frequency that corresponds to the resonant frequency. So in other words, if the resonant frequency is 10 hertz and I apply a force 10 times per second, then this phenomenon of resonance occurs. Okay, if I apply a force at 12 cycles per second, then you're not going to get resonance. Resonance occurs as a result of applying a force at the resonant frequency. And the effect of that is that the disturbance grows. So if let's say I'm an opera singer, and I sing at a really high pitch voice, and really loud as well. And that voice, the frequency of that voice corresponds to the natural frequency of a glass, of a wine glass, or of whatever glass, then I can cause that glass to start vibrating because my voice is applying a force at the resonant frequency of the glass. That causes the disturbance of the vibration in the glass to grow. The most common example, the easiest to understand example of resonance occurring, you got a swing set. The frequency of the swing set, the resonant frequency of the swing set is whatever. Well, the period is 2 pi squared over g, so the frequency would be 1 over 2 pi squared over g, right? So let's say that frequency ended up being 2 hertz. If I apply a force on that swing set of 3 hertz, watch, then the swing set doesn't go higher and higher and higher. The disturbance doesn't grow. But if the swing set is going back and forth at 2 hertz, the natural frequency of the swing set, and I apply a force at 2 hertz, what happens to the vibration of the swing set? It grows, right? Does that make sense? When you apply a force at the right rate, at the natural frequency, the resonant frequency of whatever it is that's vibrating, then that disturbance will grow. Sometimes to the point of structural failure. Like when the opera singer sings loud and high pitch, she can actually cause that glass to eventually break. Because structurally the glass can't hold it anymore. Does that make sense? Let me write that down, and then we'll show you a little video that provides you with an example of resonance occurring. So we define resonant frequency as a natural frequency at which anything wants to vibrate. Resonance occurs when a force is applied on an object at a frequency that matches the resonant frequency. Of the object. Now, what does that do? That causes a disturbance in the object to grow. The swing set. Remember the swing set. It's the perfect example. It's the perfect way to remember this. If the swing set is going back and forth at its natural or resonant frequency, and we can calculate that resonant frequency, and you apply a force at random times, then the amplitude of the swing set doesn't grow. But if I apply a force at just the right rate, if I apply a force at a rate that matches the resonant frequency, then the disturbance grows and the swing set goes higher and higher and higher. And sometimes that causes failure, like in the case of the opera singer or in the case of, well, how many people have walked across the pedestrian bridge in Okotoks? You know what I'm talking about? The pedestrian bridge by the library, the skinny one. They're replacing that this summer, by the way. Yeah. It's difficult to make resonance occur in that bridge, but you can imagine what it would feel like and what would happen if you could. You've jumped up and down on that bridge, and you can feel the vibration of that bridge, right? But you know that when you jump up and down, you can't match that. You can feel it going up and down, and as hard as you try, you can't match the rate at which it's going up and down because you can't jump high enough to do that. It's well designed. It vibrates with a frequency that is lower than anything that you could apply by jumping up and down. In other words, no matter how hard you try to jump up and down and match the resonant frequency, you can't do it. If you could match the resonant frequency of that bridge, then the vibration of that bridge, which you feel a little bit, would grow, and the bridge would start swinging up and down more and more and more. We recognize the resonant frequency of the bridge, but we also recognize that we can't make resonance occur, at least not under normal circumstances, and that's by design. They knew that when they built that bridge, when they designed and built that bridge. Go ahead.